Welcome to this explainer brought to you by Forge College. Today, we're putting on our hard hats and getting our hands absolutely dirty. We're going to take those design blueprints and command sequences from our previous lesson. You remember designing command sequences and scripts, and we're transforming them into working, runnable bash scripts right inside a completely safe local testing environment. Seriously, if you've ever wanted to know how to automate your Solana token management without, accidentally blowing anything up on the mainnet, you are in exactly the right place.
So here's our master schematic for today's build. We'll go from blueprints to scripts, set up the sandbox, handle mints and accounts, and move some tokens. Then we'll uncover the magic of idempotency and finish up with checkpoints. Let's get right into it.
All right, before we write a single line of code, we really need to understand the absolute linchpin of our entire build today. It's called idempotency. Now, I know it's a big, fancy engineering word, but honestly, you can just think of idempotency as the smart light switch of coding. Think about it. If a light in your room is already on and you press the on switch again, the light bulb doesn't just explode, right? It safely stays on. Well, in scripting, idempotency does the exact same thing. It prevents your code from blowing up, crashing, or creating weird duplicate resources if you happen to press start twice. It's literally the ultimate safety net.
Section 1. Blueprints to runnable scripts. So we're going to build our token machine using 3 very specific bash scripts, and I want you to notice the progression here. First, we sequentially construct our environment. Second, we forge our digital assets. And finally, we execute and verify our transactions. Keeping these concerns neatly separated into 3 focused files makes our whole system modular, incredibly easy to test, and way simpler to debug when things inevitably go wrong. Section 2. Setting up the sandbox. So what actually goes into that foam-padded room of ours? Well, by running the Solana test-validator in the background with a simple command, we basically spin up our very own private blockchain. But crucially, we also set up a local config directory and generate test keypairs specifically for this workspace. This makes absolutely sure that we don't accidentally overwrite your global mainnet settings, and much more importantly, that we don't accidentally spend any of your real sol. We even hit it with a massive local airdrop of test tokens, so we have plenty of fuel to play around with.
Section 3. Creating mints and accounts.
Now, handling the memory of our scripts is absolutely crucial here. When we create our new spl-token mint, the terminal spits out this long, complex address. But instead of just losing that address to the void, our script dynamically parses the CLI output and saves that brand new mint address directly into a hidden local text file. We'll call it .mint_address. This tiny little text file acts as the memory bank for our automation. So the next time the script runs, it just reads this file instead of blindly creating a second, totally redundant token. Pretty neat, right?
Section 4. Moving and verifying tokens.
Here's the thing. As engineers, we must always measure our outputs. We can't just fire off commands and cross our fingers hoping for the best. We need to map each of our 3 scripts to the exact visible logs and signatures we expect to see pop up in our terminal. When setting up the environment, we want to see the validator process ID and the localhost URL. When creating the mint, we must see those parsed addresses. And when we finally transfer the tokens, we really need to see that transaction signature and the exact snapshots of our decreasing and increasing balances. If the output doesn't perfectly match this mapping, then our script just isn't finished yet.
Okay, picture this entirely realistic scenario. Your scripts are running perfectly. Everything is great. But then, a rogue cat walks across your keyboard and executes the whole 3-script sequence a second time. What happens? Does the machine crash? Does your terminal literally catch fire? Or worse, does it just clone a million unauthorized tokens on your local chain? Section 5. The magic of idempotency.
Let's look at how this concept actually builds our defensive strategy. On one hand, a non-idempotent script just blindly executes commands. If you run it twice, it throws fatal errors or completely ruins your supply logic by minting duplicates. But our idempotent script? It's smart. It actively checks if that .mint address file exists before doing anything at all. It queries the pair's balance to see if they already have tokens before minting new ones. It gracefully skips duplicate actions and just reports a polite message rather than panicking and crashing the whole shebang.
I want to pause here for a second because this is a core philosophy in our broader development courses. We always try to emphasize that writing a script that works just once is, well, relatively easy. But writing a script that survives the real world, a script that can be interrupted, rerun, and bumped into without breaking, that requires exactly this kind of thoughtful, defensive engineering.
This is really what separates a beginner script from professional, robust automation. Section 6. Checkpoints and next steps.
Look, if things break, and honestly, trust me, they will eventually break, you need to check your wiring using a solid troubleshooting checklist. If you get an account not found error, go verify that your local config actually points to localhost and that your key pair paths are typed perfectly. If commands fail to connect, ensure your validator actually had enough time to start up. Sometimes you literally just need to add a simple 3-second sleep command to let it settle down. And if you notice your script isn't capturing addresses properly, you might have some fragile CLI parsing. You may need to tweak your awk commands or switch to a JSON pipeline to parse that terminal output much more robustly.
Listen, if you only remember one thing from this entire explainer, please let it be this golden rule. Design scripts to be observable and recoverable. Make every single mutation step report a clear success message or a transaction signature. Record your critical IDs to local files. And always favor simple existence checks, like just asking, hey, does this account exist yet? Over trying to write wildly complex error recovery logic. Just keep it simple and keep it observable. You've done an incredible job today. You have completely conquered the local sandbox, turning raw designs into idempotent working automation. But the ultimate test is still out there. Will these local scripts survive a real production deployment? Well, that is exactly what awaits you in the next lesson, where we're going to promote these very scripts into automated deployment pipelines, managing resource lifecycles for both staging and production environments.
Thank you so much for joining me in the workshop today. I really hope this explainer shed a ton of light on how to implement, test, and protect your CLI scripts. To continue exploring Web3 development and join an amazing community of builders, head over to forge.college. But before you go, I want you to ask yourself, if your local script can survive a cat walking on the keyboard today, what will it take to survive 1,000 concurrent users on the mainnet tomorrow? Think about it. We'll see you in the deployment pipelines.